Welcome back. This time we will focus on what happens if the catalyst loses some of its activity during the conversion reaction. This will of course affect the overall reaction rate and thus the time needed for the conversion of your reactant to the product. Let us first look at how the catalysts inactivate over time. The kinetics of this inactivation from active catalyst to inactive catalyst generally follows first order kinetics. So the higher the amount of catalysts, the higher the inactivation rate. This also holds for biocatalysts like enzymes or for the inactivation of microbial cells. If you put the catalyst in a batch reactor, it will be inactivated over time. Let us set up the mass balance for the catalyst, and then it reads the change in the concentration of the active catalyst is equal to the reaction rate at which inactivation of the catalyst takes place. This rate is minus the reaction constant for the inactivation times the concentration of active catalyst that is available at that time. You can solve this mass balance and you will find that the concentration of active catalyst decreases exponentially over time. If you know the value of the inactivation constant K inactive, you can predict the activity of the catalyst at any time during the batch reaction. But first, we'll start with the ideal situation in which the catalyst remains active. So in a reactor, a homogeneous conversion takes place, so the reactant A is converted into product P. This reaction follows the first order kinetics with rate constant K1. You can set up the mass balance for the reactant A, which reads that the change in the concentration of reactant A equals the reaction rate constant K1 times the concentration Ca. The minus sign indicates that the reactant A disappears. So if you assume that your catalyst remains 100% active, you can solve the mass balance and find that the concentration of reactant A decreases exponentially over time. But realize that the rate constant K1 is linearly related to the amount of active catalysts. So the more catalysts you have, the higher the reaction rate. So what if you consider that your catalyst is inactivated over time? In our batch reactor, both the concentration of reactant and the concentration of active catalyst decrease over time. Let us again set up the mass balance for the reactant A. Its change in the concentration depends both on the concentration of active catalysts and the concentration of the reactant. This mass balance has two variables, the Ca and the Ccat, that depend on time. And so the balance cannot be solved anymore by separating the variables. Fortunately, you know from the mass balance of the catalyst that the catalyst concentration exponentially decreases over time. This can be combined with the mass balance for the reactant, leaving one equation with the two variables, Ca and T, that can be separated. After separation of the variables, we can integrate and solve the mass balance for the reactant analytically. You are now able to predict how the concentration of your reactant decreases over time, while taking into account the inactivation rate of your catalyst. In this graph you see how the concentration of reactant A decreases over time. The red line represents the conversion of the reactant without inactivation of the catalyst, and the blue line represents the conversion of the reactant with simultaneous inactivation of the catalyst. So in this example, you see that about 99% of the reactant is gone after 2 hours if the catalyst is stable, the red line. But in case the catalyst is inactivated during the reaction, you see that the conversion reaction slows down and that about 15% of the reactant is not yet converted after 2 hours of time. The trend of this line also tells you that if your catalyst is inactivated, you will need to wait quite a long time before you reach 99% of conversion. The example showed how the inactivation of the catalyst influences the overall conversion rate. You also learned how model equations can help you to predict the degree of conversion over time. Try if you can use these models yourself to predict how much time is needed to reach, for example, 99% conversion. See you next time.